Now it gets good. Here we go. They open. What happens? Sodium rushes in and causes the entire muscle cell to become what?
Depolarized.
Depolarized. So it becomes what charge?
Positive 35.
It becomes positive. Because what ion came in? Positive. Do you see the yellow charge go this way?
Yeah.
That means the depolarization travels like a wave all the way across the cell membrane of the muscle, across the sarcolemma. Eventually, it's going to run into
T cells.
the T tubules.
Tubules.
Let's watch what happens. Go. This is so fun. Oh, but we can't leave it there for long, otherwise your muscle's going to stay contracted. Acetylcholinesterase, see those little Pac-Man looking dudes? Yeah. What do they do to the acetylcholine? Ate them. And it actually breaks them apart into component parts. And we need to get the acetylcholine out of there, otherwise what's going to happen to your muscle?
It's going to cramp
up. It'll stay contracted. Can't have that. So we got to get rid of the acetylcholine in the synapse. Next. There's another way. We also suck it back in by reuptake proteins, which is shown here. Watch, go, click it, this is good. Watch this, it comes in, and then it gathers, go to the next. Watch what happens here. Oh, what's that?
A
see that?
vesicle.
Candy, if you can name the process.
Endocytosis.
Say it.
Endocytosis.
Congratulations, what do you want?
Peppermint patty.
Huh?
Peppermint patty.
Peppermint patty it is. Did you hear what he said?
Endocytosis.
Endocytosis.
I missed whatever it was.
It was good. It was far distance. Okay, get out of this. Yeah, and now, click next. No, not back. Go forward, forward again. Okay, here we go. Let's put it all together now. And there's one level deeper too. Yes?
What causes the muscle spasm?
No, too early. Click that one. Can't, no, not now. I got 15 minutes. Yeah, click that. I got 15 minutes, lots to do. All right, click the sarcomere shortening and full screen it. And now just press play.
And a relaxed muscle.
Blah, blah, blah. Take a look. We have A bands, which are the entire length of, what's the purple? Myosin. I band here. Ooh, look! Wiggle, wiggle, wiggle. What's happening?
It's contracting.
Well, what happened to the I bands?
It got disappeared.
Yeah, that whole middle H zone disappeared. The A band, though, stayed
The same.
So contraction happens in multiple directions, but it'll cause the entire muscle fiber to shorten. Does that help? Yeah. Seeing how it actually contracts. Pirate accordion, right? Mm-hmm. Okay, click out. Yes?
As the H or the I disappeared?
The H and the I. The I never fully, but close.
What's the H?
Okay, click on this one. Alright, this is really high-tech animations. Okay? Click start action potential. Look at this action potential. Wow.
Whoa.
Exocytosis, acetylcholine into the cleft, attaches to receptor proteins on the muscle. What comes in?
Potassium. Sodium.
Sodium ions enter, causing the muscle to become
Positive.
We say it's called
Depolarization.
depolarization, and that travels like a wave all across the surface. Okay, good on that?
Yeah.
There's just another visualization of the same thing. Let's go, one level deeper. Get out of this, go back to the Prezi, next one down, the next Pharma Mall. Yeah, that one. Favorite animation ever. Alright, so yes, I have favorite animations. This is my favorite. So here we have our muscle fiber with a bunch of myofibrils, each surrounded by the purple thing called the what?
Sarcoplasmic
reticulum, which has what?
Holds calcium.
From here to here is?
Sarcomere.
What's this?
A T
And then the
tubule.
outer covering?
Oh.
Sarcolemma. Good, next. Alright, here, it's going to go fast. I'm just going to let it go.
Okay.
Don't freak out.
I'm going to freak out. It's not that fast. Oh.
Okay, now I want you to just press the refresh button at the top. Okay, don't press next yet, please. Or no, go ahead and press next. All right. See it again, acetylcholine, depolarization, but where did the depolarization go? Down the what?
T-tubule.
Down the T-tubule. So that means what ion is coming down here?
No,
Sodium ion. So this is where we start to put it all together. I promise it'll all make sense. You're going to be like, no way. So the sodium ions come down the T-tubule, right?
Yeah.
Well, what's this?
The sarcoplasmic
Sarcoplasmic reticulum, which I said holds what?
Calcium.
Which has what charge?
Plus 2.
Plus 2. What's the charge on the sodium?
Plus 1.
Plus.
Makes a name. Plus.
Make them do what? Two positive charges next to each other. Repel. So the presence of the sodium ions coming down the T-tubule causes the calcium ions in the sarcoplasmic reticulum to leave. Refresh it, do it again. The black diamonds on here, surrounded by the yellow perimeter, those are calcium ions. So they're each 2+, Ca2+. Let's watch it one more time. Here comes our depolarization. Acetylcholine attaches, sodium rushes in, all the way down the T-tubule, and then calcium ions leave. Where do they go?
To the other.
Back it up. Yeah, we're refreshing it. Okay, I want you to get this part, because this is the place where kids have trouble visualizing in the past. Here's our sarcoplasmic reticulum, right? And so that sodium ion comes down here, it's going to force the calcium out. So that means it gets squeezed out. I want you to view the myofibrils like sponges. It soaks up the what?
Calcium.
The calcium. So that means calcium goes deep down within the myofibrils and surrounds what two proteins? Myosin and actin. But when a muscle's at rest, is there calcium touching that actin and the myosin? No, that's what makes the muscle relaxed. So therefore, the presence of calcium must allow a muscle to contract. But the only way the calcium gets there is if we have depolarization and sodium coming down the T-tubule. Yes?
Can you repeat the thing about like the muscle relaxing?
I will in a minute.
Okay.
I promise. Okay, it's coming up on the next one. Go ahead. Yeah. Yeah, we're good. We're good. We can do this. Because now the hard part starts. There we go. That's what I was looking for. That verbiage there. All right, go. Oh boy. Here we go.
What the donk?
Stay connected. What's the blue? I know it's hard. I am pushing you to your limits. Myosin because it's
Thick.
thick. What's the gold?
The actin.
Actin. Here's something new though. Okay, the actin is made out of like 2 strands of amino acids. They're twisted around each other. It's like a twisted ladder looking thing, almost like DNA, but not like DNA. Anyway, do you see how the gold is the actin? But what's this other stuff around it?
Troponin.
I'm going to give it to you, and it's going to make you angry. It's called the troponin tropomyosin complex. Listen, troponin is the light green. The darker greenish color right here, that's tropomyosin. So it's called the troponin tropomyosin complex because they're attached to each other. It's called a complex because the troponin is attached to the tropomyosin.
They're not the same thing.
No. The troponin is the binding site for calcium. Okay, Ariel? The troponin is the binding site for calcium, which you'll see in just a second. I want you to look at the actins. Do you see these little white things right here that are kind of covered up by the tropomyosin?
Yep.
Those are the myosin head binding sites. You remember you saw the myosin heads pull the actins in earlier, right?
Mm-hmm.
Right now, the myosin heads can't touch the actin. So how would you describe the state of the muscle?
Relax.
It's relaxed. And why can't they touch the actin? Because the binding sites are being blocked by
The trial.
the tropomyosin. And they're blocked because there's no calcium. Add calcium. Watch what happens. See where it says add calcium? Click it, and watch what the calcium attaches to. Troponin changes the shape of the troponin tropomyosin.
Oh, that's cool.
What's exposed? What are these white things? The binding sites. And so if they're exposed, guess what the myosin heads can do? They can form what's called a cross bridge, where they attach to the actin, and then they move. If they move, that's going to require what? Energy. Look what's coming in. The yellow thing coming in is ATP, but it's breaking off the what?
The third phosphate.
The third phosphate. It breaks the bond between the second and third phosphate through what process?
Hydrolysis.
Hydrolysis. Now, hydrolysis occurs by breaking off that third phosphate. The energy that's released, what's it going to do? Guess what the energy does? Moves the myosin head. And so one ATP makes one myosin head move. And then what takes off?
ADP.
ADP and a P. Where do they go?
To the mitochondria.
Back to the mitochondria for what process?
Dehydration synthesis.
Cellular respiration, which leads to dehydration synthesis of putting it back together. Okay, I want to make the muscle relax. Take away the calcium. You're fired. Calcium leaves. What happened to the troponin and tropomyosin? It changed shape back and it covered the binding sites, right?
Yeah.
And then the muscle naturally will
Move back to
relax and go back to its position. I want to make it contract again. Add calcium. Calcium attaches to the what? Troponin portion of the troponin tropomyosin complex, exposing the binding sites for the myosin heads to attach to. When they attach, it's called something. Get this written down. Cross bridge. When a myosin head attaches, it's called a what? Cross bridge. What provides the energy? ATP. Breaking off the third phosphate through what process?
Hydrolysis.
Hydrolysis provides the energy to pull that actin towards the center of the sarcomere. Whole sarcomere shortens. And this is happening in millions of actins and myosins in one muscle. And all in less than 1/10 of a second. What happens when you're dead?
You stiffen.
When? And what's it called? It's called rigor mortis. And when does it set in? Do you know? It's like it sets in around 4 to 8 hours. 8 hours. It'll peak 12 to 24 hours depending on temperature outside. But what happens in rigor mortis? Your muscles actually become
rigid,
like locked.
Yeah.
Locked. You can't bend. Why?
There's no calcium.
Think.
Because there's nothing
Think.
sending the signals to relax.
Make the muscle relax, please. What just left?
calcium.
Where'd it go?
Back to the.
Back to the what? Sarcoplasmic reticulum, where it was stored, right?
Yeah.
But when the sodium came down and was kicked out, guess how it got into the myofibril? By what process do you think? It diffused in. So that means when we put calcium in to make the muscle contract, it was diffusion. So it moved from high to low. How are we going to put it back? That means we have to go from low to high, which requires energy. So when you die,
You don't have energy
you don't have any ATP, so the calcium stays
there.
in. It can't get out. If there's calcium stuck here, the muscle, the myosin heads stay contracted or connected via cross bridges, and the muscle is locked in a position because we can't get the calcium out. Why? Because it requires ATP to get the calcium back into
The sarcoplasmic.
sarcoplasmic reticulum. Yes. The sponge myofibril, because I said it was like, I wanted you to envision it sucking up the calcium. As soon as the calcium was forced out of the sarcoplasmic reticulum, it has to go deep within the myofibril to surround the actins and the myosins. And so think of the myofibril like a sponge. It sucks up the calcium. Because it's in low concentration in there, and it diffuses in.
So when it doesn't need calcium anymore, that's where it goes back.
It goes back to the sarcoplasmic reticulum to be stored again. And that's what requires the energy. Because we're pumping it from a low to a high concentration. We're putting it all back into that storage facility. Yes?
Where is the calcium? Like, it's either absorbed or stored in the sacro or whatever.
Sarcoplasmic reticulum.
Or the fiber.
Or it's in the myofibril itself and surrounding the myosin and the actin.
So is it like when it's like when you do the like when you're moving your muscle, that's when it goes to the fiber?
It goes in and surrounds the actin and the myosin, yes. When I say contract, calcium floods in, I contract. When I say relax, calcium is pumped out and I can relax my muscle. Calcium in, calcium out.
How does it get the calcium out so quick?
ATP,
But like this still seems like a
active
lot.
transport. And all the meanwhile, we're also conducting sodium-potassium pump to restore the charge, to kick the sodium out. And it's amazing. And it's happening millions of times per second. Millions. Billions. Yes?
Do you teach us how they teach us in college?
Do I teach this how they teach it?
Yeah, like
I don't think it would be
As
maybe
good.
quite as animated.
Yeah.
I'm a little
Like how
I do a lot
They
of
probably
stops.
give you
how
a
fast
rating.
you're going though? Is that like how fast?